Today we have Tyrone visiting us from Monash University, where he's a postdoctoral fellow with Dallas Center. Prior to that, he did his PhD at MBA in Garden, working with Marat Gilfinov and Rashid Sanya. Rashid was here at CITA a couple weeks ago. For that, he did master's degrees in Alberta at U of A. Today's going to be talking about uncovering the progenitors of type 1A supernovae.
That's right. Okay, thanks, Jerry. So today, mainly I'm going to be talking about type 1A supernova progenitors. Just quickly, a shameless self-promotion for something I was talking about earlier today also, in case you don't care about accreting white dwarfs. We also, in a sort of parallel development, have been working on the final fates of the most massive stars that ever lived, the probable seeds of the most massive high redshift quasars, like the Mortlock quasar, or the one that was just announced yesterday, actually. Things that reached 1 billion solar masses in the first few hundred million years of the universe. So if you want to know more about that, just give me a shout after the talk. But today, this is the problem I want to talk about. This is the remnant of an explosion that went off in the Large Magellanic Cloud a little over 400 years ago. It goes by the very, very catchy name 050967.5. You get good at phone numbers. This was a type 1A supernova, and we know that it was a type 1A supernova, actually, because we've seen, not just from the enhanced abundance of iron, from the energetics and so forth, but because we've actually seen the light echo, light from the original explosion scattered off of dust at just the right distance, that it's reflected back to us 400 years later. And so we can actually measure the original spectrum, and we know that this one in particular was a relatively normal type 1A supernova. Now, because we know it's a type 1A, there's a lot we can say about it. We know that it pretty much had to be the explosion of a roughly Chandrasekhar mass white dwarf made of carbon and oxygen. It's clear from the energetics and the nucleosynthesis. But what we can't say is why this happened. Why would a white dwarf, a relatively, dare I say, boring object, happy to sit and cool for the next many, many billions of years, why would a white dwarf suddenly undergo a thermonuclear explosion that, briefly outshines the rest of the integrated light in that galaxy combined? Well, we have a lot of ideas, but fundamentally we're not sure yet. Most of these ideas can be grouped into one or two sort of broad families. In the single degenerate scenario, or it's a bit more hip to call it accretion and merger channels now. In the single degenerate scenario, or accretion, a single carbon-oxygen white dwarf grows through nuclear burning at its surface, either intermittent or persistent, until reaching the Chandrasekhar value or some limiting value. Maybe you detonate a helium layer on top, triggering an explosion, something you hope looks like a type 1A. Alternatively, in the double degenerate scenario, or the merger scenario, you have, by various means, a pair, usually, just a pair of naked carbon-oxygen white dwarfs shedding angular momentum through gravitational wave radiation until they inspiral and merge, producing, hopefully, something that looks like a type 1A supernovae.
Don't you have an accretion also from a double degenerate scenario?
In principle, if you have steady mass transfer, or there's other ideas like Noam Soker has a core degenerate scenario where the one is actually the core of an AGB, and you have an envelope around both of them because you have like a common envelope event. There are many, many varieties within each of these. And you might say, well, okay, either way, it seems to make a type 1A supernovae that usually follow the Phillips relation. Do we really care? Well, first of all, if you want to nail the evolution or not of dark energy down to better than 1% in the local universe, well, below redshift 2, it would help if we actually knew if we could map from the spectra or from the light curve to what the actually was exploding. But more generally, this matters for questions like nucleosynthesis. You get different abundance ratios of the elements if you have the explosion start at the core of a Chandrasekhar mass carbon-oxygen white dwarf versus if you have a merger. For instance, the abundance of manganese relative to iron seems to be favoring a significant fraction of something that looks kind of like a Chandrasekhar mass explosion, although there are ways you might be able to get this with simmering in a merger. And more fundamentally, this is just a ridiculously long-standing problem in binary stellar evolution. I mean, you need to bring a compact object into a close orbit with some kind of donor. that screams common envelope evolution. We can't understand where binary black holes come from until we understand this much more basic case of binary stellar evolution, common envelope evolution. So how can we tell the difference between these two scenarios? Well, we need to go looking for possible progenitor objects or either direct or indirect signatures of these types of objects. So for the accretion scenario, the single degenerate scenario, what these are actually going to look like depends on, basically what accretion regime you're in, and varies softly as a function of mass. So for relatively low accretion rates, sort of nuclear time scale accretion rates of matter from the donor.
What is it, helium or hydrogen?
So this is for hydrogen. You could also be accreting helium. We'll get to that later. So this is, for now, your standard, most vanilla picture where you're accreting from some hydrogen-rich donor. So I'll talk first. We'll talk more generally later. But
If you just accrete a bunch of hydrogen, won't you just rejuvenate? So won't it just seem like a red giant?
depends on the accretion rate. So below a certain accretion rate, what happens is before you trigger nuclear burning, you don't immediately trigger nuclear burning. You don't get the necessary temperatures and densities. You build up matter until in an envelope, a thin envelope, until triggering an explosion in partially degenerate material. And you get sort of this classic thin shell instability, like from normal single stellar evolution. And what happens is instead of steadily burning, it just erupts and blows that off. These are contours of envelope mass that you need in order to build up in order to trigger that detonation, explosion. For this upper bound, so above that, you're accreting fast enough that you can actually burn all of this material at the same rate you accrete it steadily through CNO burning. But the upper boundary here is where you once again satisfy the core mass luminosity relationship for giants. Above these luminosities, because your luminosity is that of nuclear burning of this material, your accretion rate translates directly into a luminosity. Above this boundary, it's not immediately clear what happens. So on the one hand, you don't have any thin hydrostatic solutions anymore. So presumably on at least a thermal time scale, it should become a giant again. If it becomes a giant again, it's probably going to envelop its companion. You're not really going to have, you're going to have a common envelope. You're not going to have a single degenerate progenitor anymore, at least in the traditional sense. On the other hand, you might have some dynamical effects that could moderate this on shorter time scales. Hachisu, Kato, and Emoto have a whole bunch of papers about how there's this opacity bump due to iron of around 1.5, 2 times 10 to the 5 Kelvin. You could blow off an optically thick wind that stabilizes mass transfer and kind of keeps you hugging close to the maximum of the burning strip. But the punchline is anything up here, it either becomes a red giant and it envelops its companion, or it's blowing an optically thick wind, which is not a terribly efficient way to grow a white dwarf. And I can talk a lot more about constraints on this regime. Below this steady burning strip, it's very, very hard to grow the white dwarf because, again, you're blowing off a lot of your envelope. So the most efficient regime to actually add mass onto a white dwarf is this steady burning strip. And so generally, this is what people invoke when they're invoking an efficient accretion scenario, at least a significant amount of time in this steady burning strip. So what do these objects look like? Well, we have observed counterparts, the super soft sources. And we see them in the LMC, the SMC, and along a few lines of sight where the column density is mercifully low. And I say that because while these things have luminosities on the order of 10 to the 37, 10 to the 38 ergs per second, their effective temperatures are in the neighborhood of 10 to the 5, 10 to the 6 Kelvin, with pretty remarkably close to blackbody spectra. You see edges from carbon and oxygen way out in the Wien tail, but below that, as far as we can see, and certainly from models, it looks like it's pretty close to blackbody for most of the emission. So we should be able, so we've seen, so anyway, so this is, most of the emission will be fairly strongly extincted by intervening H1, but we can see the Wien tail, and we found a number of these objects. For the double degenerate scenario, the easiest answer is just to say, well, we don't see any of this, right? It should look like a pair of boring white dwarfs until suddenly they merge and produce an explosion. Now, there are a bunch of caveats to this. Your merger doesn't necessarily have to lead immediately to an explosion. You could have a simmering phase. You can have a brief supersoft source phase. Josiah Schwab et al. Has been, merging white dwarfs in MESA, just in simple 1D calculation, and showing, look, you should have a big fluffy object that has to cool, and as it cools on a thermal timescale, it spends maybe 10,000 years as a supersoft source. On the other hand, those ones don't seem to explode, so it's not quite clear what the observational signals should be. I will say, however, that a number of people have gone out and tried to find double white dwarfs in the Milky Way, looking at SDSS, looking at other places. There's a SPY survey, and it looks like there's at least enough, Danny Maz will say maybe even 10 times more, double white dwarfs merging per millennia than you would need in order to match the type 1a supernova rate, which is far from a proof, but at least it's a qualitative statement that this isn't crazy. So what's the most obvious way otherwise to try to distinguish between these two things? Well, we can try to look with temperatures like this. We can look for that Wien tail in the soft X-ray band. So we can try looking first for individual objects. So one way to do it, you wait and you hope for a supernova to go off somewhere close by where Chandra or XMM has already looked. And then you can go back in the archival data and see if there was an X-ray source there. So Mikkel Nielsen wrote a whole bunch of papers trying to do this. Other people have tried as well. You have to be very lucky because you have to wait, and also for a supernova to go off nearby, but also you're assuming that this phase was immediately prior to explosion. There's really nothing you can do otherwise. So that's a problem. And most of the supersoft sources that we do know of are also not persistent. They tend to vary, right? So it's interesting, but it's difficult to say if this is constraining. Also, most supersoft sources that we do see tend not to be, it's easiest to look in the soft X-rays if they're at the highest end of this temperature range. But the problem is most supersoft sources that we do see tend to be kind of more towards the bottom end, and that's because they don't have radii consistent with just cold white dwarfs. You have this fluffy photosphere on top of it, heated photosphere. So that is tricky, relies on luck. Maybe we give up on individual objects. Maybe we can look in the X-rays for populations, right? And so this is what Mara Gilfanov, Rosanne DiStefano, and others tried to do. The best way of going about it is to look not for numbers of objects, but for the total integrated emission. This is because there's a cute trick here. Whether a few white dwarfs accrete very quickly or many accrete very slowly, whatever the mechanism is, if you want to bring a certain number of white dwarfs up to the Chandrasekhar mass per unit time, or whatever your explosion mass is, then you need to accrete a certain average mass per unit time per white dwarf. And since the luminosity of these objects in the steady burning regime is just going to be set by nuclear burning of that material, that gives us an estimate in an average sense of the total luminosity of any large population of nuclear burning white dwarfs. But again, the problem is we're not exactly sure. Again, most white dwarfs seem to have fluffier atmospheres. Most of the emission is coming out in the extreme UV. And also, in principle, not saying this is plausible, but you could enshroud objects in some circumstellar medium excess that would completely obscure the soft X-rays. They're very, very easily absorbed. And so, while it's interesting, this argument really didn't quite convince everyone, especially in light of arguments like the need to produce a manganese would be nice. So with that in mind, the question is, how can we go on from here? How can we take this and say, all right, let's let's find some other way to account for these things. The fact that most of their emission is coming out in the extreme ultraviolet, and they could have, circumstellar material. There was a previous common envelope and so forth. And the X-ray phase might be significantly delayed from the actual explosion, and still constrain the luminosities and temperatures of these objects. This is basically everything I just said. So the idea is to look for these things not directly in soft X-rays, but to consider them as the extremely powerful sources of ionizing radiation that they are. And in fact, we know that at least a few accreting nuclear burning white dwarfs have associated ionized gas. The prototypical example is Cal-83 in a large Magellanic Cloud. Very strong, it's not something you could easily miss. It has emission line ratios that look like a planetary nebula, very strong Helium II, strong O3, but it's 10 parsecs in size. All right, so we can look for these things as ionizing sources. Where should we look for them? Well, the trouble in star-forming galaxies, like the LMC, etc., is that if you want to look for a population of these objects, well, next to O stars, they're not that important, right? A few O stars are going to totally dominate the ionizing radiation budget in a given galaxy. But in passively evolving, retired galaxies, red and dead galaxies, there's really not that much to compete with. There's post-AGB stars, etc. We'll get to that. Here, your accreting nuclear burning white dwarfs have a chance. And that's great because, contrary to what you may have thought 30, 40 years ago, retired, passively evolving early type galaxies are not without warm, diffuse, ionized, and neutral interstellar medium. And we think we have a pretty good handle on what's actually doing the ionizing in many of these galaxies, in those where we can exclude any kind of low luminosity AGN or things like that. In many galaxies, it's the old stellar population itself, post-AGB stars and things like that. So because this is a well-developed theory, there are a lot of models for what this should actually look like. This is somewhat out of date, but still pretty much right. Bruzel and Charlot estimates, spectral synthesis calculations. And what I've shown you is just in arbitrary units the flux as a function of energy. Here's the H1 and Helium II cutoffs in the spectra. And the three different lines, note they're basically on top of each other, are for a population at 1 gigayears, 3 gigayears, 10 gigayears.
What's Sauron?
Mm-hmm. Sorry?
What's Sauron?
Sauron is a emission line survey. Yeah. And Khalifa is sort of the successor to that. That's Mark Sarzi, big Lord of the Rings fan. Right. So this is what we kind of expect the ionizing background in an early type galaxy to look like. The question is, all right, what would it look like if the progenitors of type 1a supernovae in these galaxies were coming from accreting nuclear burning white dwarfs? So I'm going to start with a toy model, because I think toy models are nice and illustrative. So let's just start by saying, okay, we have this, we're not sure how inflated the photospheres are. Let's just say they're all at one temperature. We'll generalize it in a couple slides. Let's say they're all 2 times 10 to the 5 Kelvin. That's sort of a typical supersoft source temperature. And we know what the luminosity of this population should be, because we need to actually match the type 1a rate. And we know that there's no strong cutoff until you get way out into the vene tail, where you see these carbon and oxygen edges. And what we find is that this is again for 1, 3, and 10 gigayears. First of all, huge evolution with time. Second of all, significant enhancement in the hard ionizing background, Helium II ionizing emission. We should be able to tell the difference between these two. We can sort of quantify this in a leading sort of way by looking at the.
So go back a second.
Yeah, sure.
So do these population models include the low mass X-ray binaries and so forth?
That's another. So that will be another bump here.
Yeah, exactly.
So this is not even including everything, right? So there's already some unaccounted for budget in the the high energy regime. So actually, Mark Sarzi and the Sauron people there, they considered LMXBs as another source of ionizing radiation because it's not sure what the lifetime of post-AGBs is, right? And it was only coming in at sort of the 10% level. But it's already, there's a perturbation there. There's something there that you need that on top of all of this. So there's even less room than I'm leaving here. So here I've just quantified, just for our toy model here, as a function of delay time, the ionizing photon luminosity that you expect to produce per unit mass for ionizing hydrogen and for ionizing helium. And you see this huge enhancement, as you would expect, in the Helium II ionizing luminosity. It ramps up because it's just following the delay time distribution inferred for type 1As, which goes as 1 over T. So this suggests an obvious diagnostic to check whether type 1A supernovae progenitors really emerge through some kind of hot, luminous, single degenerate channel, is to look for emission lines of Helium II. Strongest observable Helium II line would be the 1641 in the UV, but I'm going to focus on the 4686 line just because there's lots of optical data around. And in principle, you haven't seen, naively you might say, well, okay, no, there's no Helium II in early type galaxies, but it is an intrinsically weak line, and we are dealing with warm diffuse ISM, so we should, we can quantify how worried we should be about this. So we can plug our spectral synthesis calculations into a photoionization code, like mappings or cloudy. And we can run a grid for all different temperature nuclear burning white dwarfs with and without the underlying post-AGB population, and come up with a nice parametrization for the 4686 line luminosity we would expect for a given galaxy for an arbitrary temperature nuclear burning white dwarf population for some assumption about how much mass needs to be accreted per white dwarf. And I normalized it to 0.3 solar masses here because the maximum mass that you can make a carbon-oxygen white dwarf at is 1.1 solar masses, and the Chandrasekhar mass is 1.4. Most white dwarfs, of course, are not born at 1.1 solar masses, so this is a conservative estimate. Now you have these annoying dependencies on the covering fraction of the gas, how much ionizing radiation just escapes versus is intercepted, and the total mass of the galaxy. You can get rid of these if we just normalize our prediction to some other convenient recombination line. Most obvious for 4686, H beta, right? It's nearby, so you don't need to worry about reddening. So like I said, Helium II is a annoyingly intrinsically weak line, so we want to get the best measurement we can. So intuitively, the first idea is, okay, well, let's start by stacking. We can go to individual galaxies later. We need to be careful with that, of course, in selecting only the reddest and deadest galaxies. No low luminosity AGN, no residual ongoing star formation. So I asked my good friend Jonas Johansson, who was at MPA at the time, to kindly stack 10,000 such galaxies from the Sloan Digital Sky survey for me. There's a number of selection criteria here we can go through. Basically, you only have a fixed size fiber aperture for SDSS. So you want to look far enough away that you're not just sampling the nucleus of the galaxy, but not so far away that it's too faint and you just got noise. Similar here, you have a minimum cut on the amplitude signal to noise for measuring your lines, and criteria on the equivalent width and N2 to H alpha, which brings us to this diagram. This is the WAN diagram. I don't know if people are familiar with this. So this is sort of a standard diagnostic criteria. It's sort of next step from the BPT diagram, basically separating star-forming galaxies from AGN from things that don't have either going on. So the equivalent width in H alpha here, this is basically a measure of, in some sense, so luminosity and covering fraction at the same time. So that's why you have these ionizing luminosity. So that's why star-forming galaxies in AGN are all up here. And then N2 to H alpha basically sort of quantifies how hot the gas is. O3 to H beta would be better for that, but it's not as strong as the N2 to H alpha lines. And in any case, what we're mainly concerned with here is separating out our retired galaxies from these AGN and star-forming contaminated ones. So we took these galaxies, broke them up into bins of mean luminosity-weighted mean stellar age, and looked at the Helium II to H beta ratio in each. And that's what I plotted here. In black, for two different assumptions about the star formation history to give you the same measured age, is what you would expect for a sort of token single degenerate model. We can play around with the temperatures. We'll do that in the next slide. In red is just the old stellar population alone. No fine-tuning, not twiddling anything around. Using the ionization parameter inferred from the O3 to H beta ratio, but otherwise just out of the box. And it lines up almost perfectly. There is just no room for this huge population of ionizing sources. So we can ask, all right, how far would this have to be tuned down? Maybe they don't all come through an accretion scenario. Maybe it's just a fraction. Or maybe they only spend a very small amount of time accreting as hot luminous sources. Well, the constraint varies as a function of temperature. But everywhere it's of order, well, certainly for temperatures typical of observed superstar sources, it's of order a few percent, and going up to maybe 30% just from the Helium II to H beta ratio alone. Now, if we want to cover this area, we need a different line, because the problem is over here, you would intuitively think that as you go to higher and higher source temperatures, you would want to look for more and more ionized, higher and higher ionization state lines. But it's actually the reverse. You want to look for low ionization or neutral, or forbidden lines from neutral gas when you're trying to constrain or look for emission lines ionized by very high temperature sources. And the reason for that is, this is just H2, abundance of H2 versus a fraction of the total hydrogen. And this is neutral nitrogen, just as one example of a line that produces a strong forbidden emission. In solid here, I've shown the profile as a function of depth into a cloud for so the ionizing sources here. For I think it was a 10 to the 5 Kelvin source, so relatively a strong ionizing source, but not ludicrously strong. You get that with some O stars. And in the dashed lines, I've shown it for a 10 to the 6 Kelvin source. And you see, you have this much extended Strömgen region. So what's going on here is, for the higher temperature sources, you have higher energy photons. They penetrate deeper into the cloud. They have a longer path length. And so that bleeds out your Strömgen boundary. And so the best way to look for these things is to look not for ever higher ionization state elements, but for things that trace this partially ionized or a region where the gas is still hot but relatively neutral. Nitrogen and also oxygen have a first ionization potential that's 13.5 eV versus 13.6. So we can use these lines, for instance, O1 to H alpha, in order to get an even better constraint. We did this a year or two later. And we see there's just no room to order a few percent of the type 1a supernova rate. If we want to instead say they insist that all type 1a's still come about through some kind of accretion scenario, then what you can do is turn this into a constraint on how much mass could be accreted in a hot luminous state. And this comes out to around 0.005 solar masses. Whatever the progenitors of type 1a supernovae are, they are not hot and luminous. Now, before I go on, I just wanted to draw your attention to this part here where we're constraining. Here I've shown this as a fraction of our constraint on the luminosity as a fraction of the total type 1a supernova rate. But this can also be interpreted just as a constraint on the ionizing luminosity as a per stellar mass. produced by an old stellar population. Now, if you want to do this for something other than black body, okay, you have to rerun everything with a different spectral shape. But the point is, in principle, you can constrain things other than just nuclear burning white dwarfs. LMXBs, for instance, as well. There's Tassos Fragos, for instance, and others at Brett Lemmer have been arguing for some big uptick in the LMXB population per unit mass at relatively young stellar populations, things that are 1 gig-year to 3 gig-years. That's going to cause problems. I didn't think I'd have time for it, but I should mention my student Hailiang Chen has been doing lots of work on this with population synthesis using MESA to actually calculate the response of the donor stars in detail. Right. So that's populations. But if we want to, populations are relatively late delay time. So I mean, roughly half of all type 1As are happening after 1 gig-year in your delay time distribution. But what about everything over here? What about these short delay times? Well, we run into that problem again if we want to do this on a population scale, that there's lots of other stuff going on in star-forming galaxies, right? And so you can measure the Helium II flux, but that's obviously not just coming from accreting nuclear burning white dwarfs. So one idea is to start looking at these guys individually, trying to find individual sources. And again, I'll come back to Cal 83 as sort of the prototypical example. So again, this is in the Large Magellanic Cloud. It's about 10 parsecs or so in diameter, 15, and very, very luminescent 4686 angstrom emission, 01 6300 emission. This sticks out like a sore thumb. Other accreting nuclear burning white dwarfs, not as much. And it's mainly, as we'll get to in a minute, an issue with the sort of typical surrounding ISM densities. But the really cool thing about this is that, like I said here, like I show here, so this is the surface brightness, in this case 03, a particularly strong line, as a function of radius for for typical super soft source parameters. So a 3 times 10 to the 37 erg per second source, temperature of 5 times 10 to the 5 Kelvin. And it's worth, and the really interesting thing to note about these is that they will survive even after the source turns off, say, because it explodes, for of order the recombination time scale in the ISM, which, for 1 particle per cubic centimeter gas, is of order 100,000 years. So that means we should be able to find these nebulae around the remnants of historical type 1A supernovae.
But how much energy do you have in ionizing? How much energy in ionizing radiation do you need to produce this ionized sphere?
So the flux is of order, so the luminosity of these things is almost all in the ionizing regime, and it's of order 10 to the 37 to 10 to the 38 ergs per second. This is for 3 times 10 to the 37.
So that's less than the energy that you get just in the breakout, the short breakout from the supernova.
But most of that is now going into ionizing photons.
No short breakout?
It's very, very, very line blanketed for type 1As, yes.
Well, I haven't seen short breakout, so it's hard to tell.
No, but in the models. And in any case, people have tried to do that, so you'll get some flash ionization, at least if you believe spectral synthesis. You'll get some flash ionization. It ionizes a very tiny Stromgen sphere. It's swept up by the remnant. By the time we're looking for these things, I'll get to Tycho's supernova in a second. That's 445 years old now, as of a couple weeks ago. What the supernova could have ionized is completely swept up. There is a complicating factor in that you have the shock, the expanding shock will produce a skin of ionized gas. And you have to account for that if you actually find something, but we'll get to that later. Right, so trying to find individual objects, the trouble, like I said, is that the ISM is a multi-phase beast. You've got some, half of it is sitting at densities of around 100th, 10 to the negative 2 particles per cubic centimeter. Half of it is in the warm, neutral warm ionized phase, 0.1 to 1 particles per cubic centimeter, and a few percent is in the cold neutral medium and in the so filling factors I'm talking about here. So how much of the volume is in cold neutral gas and molecular clouds and so forth. So it turns out that this actually justifies why Cal-83, sitting in relatively overdense gas of order 10 particles per cubic centimeter, sticks out like a sore thumb, but most super soft sources don't seem to have a very strong surrounding ionized nebulae, just because most of them are sitting in low density ISM. But the nice thing, if you're looking for relics surrounding a supernova remnant, is that the supernova tells you how dense the gas is, because you know how much gas has been swept up and you can model the shock. So we're doing this now, looking for both faint nebulae around other supersoft sources, as well as emission surrounding Type 1a supernova remnants. So Alejandro Clocchiata and Armin Rest have a program. They did a night of observing with Magellan Bade, also working with Ivo Seidensal with some IFU data. And I want to stress that this is going to be important regardless of the outcome for all of these objects. Because if we see nothing, then we can rule out to very, very deep limits, and limits that are very easy to reach as a function of density, even if we don't know the density. We can rule out sort of your standard accreting nuclear burning white dwarf. And if we do find some relic nebula, robustly measure it, then we can measure the luminosity and the temperature of a historical Type 1a supernova. And just as a sort of case example, this is the part of the rim of the remnant of Tycho's supernova. This was measured with KPNO, the 4-meter telescope, I think actually 17 years ago or so by Parviz Gavamian. And I want to stress this particular one because we learn a little bit extra about this and many other Type 1a supernovae by looking at it in the optical. So this is focused on the H-alpha emission. And we see this very prominent rim along the northeastern northern front. What's happening here is neutral atomic hydrogen is being collisionally excited. There's a broad component, which comes from fast protons stripping electrons off of the neutral gas ahead of it, and a narrow component coming from the swept up warm ISM, neutral ISM though, being collisionally excited. And it turns out this gives a very, very strong constraint on the neutral fraction in this gas. You know it has to be significant neutral gas, and in fact it needs to be of order in the neighborhood of 80% neutral. Now the remnant is only 445 years old. And as I said, the recombination timescale in the ISM is of order 100,000 years. So if there was a hot luminous source there prior to the explosion of Tycho's supernova, this gas should not be neutral. So it's very easy to just take your Astro 101 Stromgen radius and say, all right, for typical supersoft source parameters and typical warm ISM, this should be ionized out to 30 parsecs. The size of Tycho's supernova remnant is presently 3 parsecs. So to do this in detail, again, you have these broadened Stromgen regions, so you actually need to run a photoionization calculation. But the limits that this puts on the progenitor of Tycho's supernova reach orders of magnitude, well, at least one order of magnitude, and really for theoretical models, orders of magnitude below anything we expect for an accreting nuclear burning white dwarf. So in black, I've shown, earlier I had Nomoto's models here. Competing group is Bill Wolf and Lars Bildston's steady burning nuclear white dwarf strip. They basically, they agree within a few percent. And in the squares I plotted just a few observed supersoft sources from the LMC. I could put them all, but they kind of overlap on each other. Just in defense of the models, this one that doesn't quite agree here, that's Cal-87, and we're looking at that one more or less edge on, so the disk is absorbing some of the emission. This line, for kind of an overestimate really of the surrounding ISM density, is what would be permissible, below this, for a range of effective temperatures is the luminosity that would produce a smaller Strömgren sphere than the present size of the remnant. And in fact, it's so far down that it excludes not just nuclear burning on the surface, but even emission from a standard Shakura-Sinyaev disk down to accretion rates of order 10 to the negative 8 solar masses per year. So that rules out even recurrent novae down to the limit of what we think can actually allow the white dwarf to grow. So whatever produced Tycho, it was not a hydrogen accreting white dwarf, and probably not a helium accreting white dwarf, because the disk argument doesn't care about whether it's accreting hydrogen or helium. So this was published earlier this year in Nature Astronomy. So we're doing this now for a number of other remnants in the LMC and in our galaxy. For many, again, the Balmer-dominated emission simply excludes any kind of hot luminous source, although not always without caveats. And so we need to go back and like I said, with Armin and with Ivo, doing looking for other emission lines, because the problem is for these very hot sources, you can have very extended partially ionized regions. And of course, many of these remnants are much older than Tycho. They're of order 1,000 years, even 10,000 years. And so they're probing an area that's a bit further out. But pretty soon, we'll have a good idea of how many, if any, and I think maybe a few, nearby Type 1a supernova remnants had hot luminous progenitors. And we'll measure for the first time their temperatures and luminosities. So I'll stop there. Thanks.
Time for questions.
Yeah.
So you touched a bit about this point previous slide, but there's this idea, so the proponents of the single degenerate balloon, their way of explaining the absence of the remnants is that the idea that by the time that you lose mass through Rushlow overflow, but by the time that it accretes, the primary has already become a compactor of some sort. How would these, how would this idea impact on your work?
Sorry, it's already been.
You're thinking spin up, spin down.
Yeah, is that what you're getting at? So the idea is a white dwarf, if it's accreting matter, it should also be accreting angular momentum. And this would...
No, talking about the idea is one of the problems with the single generators is you don't see the companion. And the companion is not supposed to be...
Yeah. Oh, you're saying that, okay, no. So you're saying that it becomes a white dwarf, the companion. If it's become a white dwarf, that means there has to be some delay between the explosion and the accretion phase. So the only way to, well, the standard way to induce this delay is that the white dwarf, while it's accreting matter, is also accreting angular momentum. And accreting angular momentum means you add extra rotational support that can hold it up beyond the Chandrasekhar mass. And then it spins down and explodes, but by that point, say the companion has evolved or whatever. So in principle, this constraint does not rule that out for Tycho. But Tycho was a completely normal Type 1a supernova. We know because we've also seen the light echo for Tycho. So if Tycho was a spin-up, spin-down scenario, it stands to reason most other Type 1a supernovae should. And the problem then is, where are all of these rapidly spinning white dwarfs? People invoke delay times of order a gig a year. There should be lots of rapidly spinning white dwarfs around. And Rosanne de Stefano had a good paper on this in 2011, 2010, showing we wouldn't have missed them. They would be luminous, right? They're not around, so it's a problem. There are other technical issues with the spin-up, spin-down scenario. It's hard to make it look like a typical, this still fairly rapidly rotating white dwarf, even though it's been spinning down. Hard to make it look like a normal Type 1a. But I think the population argument is enough of a problem.
Any questions? I have a question.
Yeah.
In your selection of galaxies,
Yeah.
you picked all when you fired old, red, and dead, and then said they're basically all double degenerate. If I understood correctly.
Well, I'm saying they're not hot and luminous is the most politically careful way to do it. So
Is your selection introducing bias in terms of the channel for Type 1a?
So you're worried that you'd be producing a bunch of H alpha and so forth from a single degenerate population in some other galaxies.
Might be earlier, I guess, right?
Yeah.
Young bias.
Yeah.
Yeah. The thing is we know they're earlier. So if they're there at all, single degenerates are there earlier from population synthesis. This has come out since. So the idea was mainly to focus on just let's get a definite idea for the late time, because some people still try to make it work at late times. But you could have some kind of, from the emission line diagnostic, I suppose if there was a significant accreting nuclear burning white dwarf population, you could get some contamination in the H alpha. But then there would also be other weird lines, and we would have picked up these galaxies, right? I mean, so a red and dead galaxy, but with a bunch of single degenerates, wouldn't just have some H alpha, and we checked this. Not as much H alpha as put it up into the star forming regime, for instance. We checked the typical equivalent widths. They were a couple orders of an order of magnitude too low, so they would still show up in our criteria. But they would also look like strong Helium II emitting galaxies, and we just don't see that. But I see your question, and we checked that. Yeah, there's the equivalent width in H alpha would still be below that cut.
All right. If there are no more questions, then let's thank Tyrone again.